before we start, can I get a quick kind of show of hands? By the way, I'm going to say ZFS. I'm going to try and say ZFS, but if I say ZFS, I mean ZFS, and you can just laugh at me. It's just something I'm going to keep trying to switch in my brain. So who has used ZFS before in their professional life? Okay, we're going to take it a bit slow. Good, this is good. It seems it's pretty popular right now amongst the conversations that people are trying to run brokers on Kubernetes or a similar like managed kind of platform. Could I ask who here is using a broker in something like Kubernetes or Nomad or Mesos or whatever else? A couple of you. Okay, we need to talk afterwards. I disagree very much. But the bad news is, depending on how your infrastructure is set up, ZFS might be hard to introduce in that environment, right? It might be possible if you do things, if you get your custom machine set up right, but without that, it's a bit tricky. It definitely is, in this talk, I'm aiming to discuss kind of very particular machine configurations that are optimized for brokers and brokers. I won't say brokers only, but you definitely don't want to run like a random application next to your Kafka broker in this case. Okay, let's get started. Kafka on ZFS. Let's go. I'm going to start with the initial takeaways, so you know what you're going to get out of this talk. If you feel like tweeting about these, I would not discourage this. So let's go. When someone asks you what this talk is all about, what are you going to tell them? You're going to say, I learned 3 things. ZFS makes Kafka way faster. It looks really cool. ZFS makes Kafka really cheap somehow, which I suppose is important if you get paid on savings. Who here has like saved their company money by resource optimization in the last year? Okay, and who here got some sort of personal benefit out of doing so? Okay, where do you work? Can I come? Yeah, okay. It does make things cheaper. It can. It definitely gives you options to do things cheaper. Whether or not you choose to is up to you, but it's an option, and that's important. And the biggest takeaway is throughout its storied history, ZFS has topped around a bit. We'll cover this in a bit. But fundamentally, it's pretty stable on Linux right now, and it's pretty stable on a platform that you can get Confluent support for. Now, they don't support ZFS. They look at me strange when I say I've got a problem, and they say, what's this thing running? So that's ZFS. Don't you worry about ZFS. No, the problem's in Kafka. It's over here. But you can have Confluent support and use ZFS at the same time. I'm not working for Confluent, so if I'm wrong about that, it's up to you to work it out. But I'm pretty sure I'm right. How are we going to do all that? The core takeaway, like the serious technical core takeaway of all of this, is that ZFS increases the amount of page cache hits your broker will experience. What the hell does that mean? Another poll. Who knows what a page cache is? Okay, right room. Awesome. To those who don't, I'll introduce it in a bit, but basically it's a way for the operating system to store some of what's on disk in memory. If there's some memory lying around that's not being used, then it means I'm just going to store this here. So if I have to read it off again, I don't have to go to disk. I can go from memory. That's what a page cache does. ZFS has fancy algorithms and other tricks that allow this to be increased a lot. And when your broker is running in a day-to-day operation, it's going to be servicing lots of writes, lots of reads. The writes obviously have to go to disk eventually, but the number of reads that can be served from memory, because through some mechanism you've been able to determine that this data should be in memory prior to it being requested, is the hit rate. So number of times you could serve from memory versus number of times you have to go to the disk, right? That's the key metric. It's the key takeaway from this whole talk. Your broker page cache hit rates affect performance hugely. Secondary to that is some tricks ZFS has up its sleeve where it comes to I/O devices. So ZFS has a history we'll get into later on, but it's pretty comfortable running drives, old spinning disks, which we don't really have anymore, but it's got things like queue mapping and request reordering and all sorts of fancy features. But it's also got some features that allow us to use some of the particular treats we get in cloud infrastructure, particularly temporary instance disks, which is they're on Azure, they're on AWS. Your machine will have so many gigs of like an SSD attached disk that's just local to you. It's not backed up, it's not migrated. If your machine moves, that data is gone. But ZFS can use this as kind of a secondary cache. So if you think of your broker normally having, let's say, 32 gigs of RAM, the instance SSD on that machine might be 100 gigs. Right? And if you can use that as a secondary level page cache, then sure, it's not as fast as main memory, but it's sure as hell faster than all the way to disk. Then your page cache hit rates, well, they're not going to change. But we have another variable here, it's called like your secondary cache hit rate. And then if you look at those two things together, you're like, overall, what did I have to go to the slow path to get that rate should go way down. So that's something ZFS can do, and we'll talk about that in a minute. And lastly, ZFS has ways to make use of multiple virtual disks that we can get in cloud providers, which allow us to basically maximize our disk I/O on a cloud instance. I'll show you some graphs later on, but you can get 16,000 IOPS for like what, $30 a month or something if you stripe it right, and you're looking at easily sending 500 megs a second to disks costing you $30 a month. Right? So that's pretty cool. We're going to go through all of that. So those are the takeaways. For your boss, faster, cheaper, we can use it now. For your friends and curious people, or if you've got a boss who likes this sort of stuff, then you've got a good boss. So that's your takeaway. Intro time. Hi. I'm Hugh. I'm responsible for Kafka at jet.com. It's an e-commerce site you should check out. We have an office in Hoboken, New Jersey, and an engineering office in Dublin, which is where I'm from. My rants, complaints, opinions, assumptions, and negative opinions about other people's technology are all my own. Jet has no opinions on this entire talk. It's important that I say this. And as I said, I might say ZFS because it's the right way to pronounce it. I don't know what you guys are doing. But I'm going to try and say Z, and just know that I mean the other one. Whatever one you think I should be saying, that's what I mean. All right, overview. What don't you know already? First question, is Kafka Redis? Hands up if Kafka is Redis. Your hand should be doing this, right? Because that is the correct answer. Kafka is Redis some of the time. Let's answer. All right. Betteridge's law of headlines, if you're not familiar with it, states that any headline that is a question can be answered no. This remains true. Let's look at what Redis is. Well, is Kafka Redis? Firstly, let's look at the spelling. Like, none of the letters are the same. To be fair, it's the same length of the string, right? But otherwise, it doesn't look like it's the same thing. If we look at redis.io, it will tell you it's an open source, in-memory, structured. You can read this yourself, right? But look at the things I've called out. So it's open source. Kafka's open source. It's a message broker. That's definitely what Kafka sounds like, right? Built-in replication. Yeah, that's a thing we've seen. LRU eviction. I don't know about that. That sounds weird. Well, that just means least recently used, which you can basically think is like a retention bytes or retention size or something on a topic. So, okay, that's about the same. Transactions. Well, we have those now, right? Maybe. Who uses transactions, really? No one? Yeah, no, it wasn't. Transactions for a different market. I'm glad we're together. I feel this is the right route. On-disk persistence. Okay, Kafka has that. Redis is lying a bit. And most importantly, most importantly, high availability. Right, so let's compare this to Kafka. The only real difference between all those emboldened white ones, because Kafka does share all of that, and Redis is the in-memory factor. That's Redis's core, and memcache and other things like that, right? Or Varnish, I think, as well. In-memory is the important thing, and that's what distinguishes, I think, in many ways, a Kafka-style system from a Redis-style system. So let's wonder a bit about why Redis limited itself to being in-memory only. For completeness, the on-disk persistence for Redis is like a backup system. It doesn't serve requests from disk. It's just if it comes back up after a crash, it goes, oh, okay, fine. Don't have to replicate everything. So why did Redis decide to limit themselves to memory? It's really fast. I don't know. Memory access times are nanoseconds, I think. Don't quote me. They're definitely faster than disk, right? That's unquestionable. Memory is fast. Memory is also consistently fast, whereas a disk can be a bit jittery based on if there's other load on it or if it's shared hardware or something. You're not really going to see, in my experience, any sort of contention issues on your memory access if you're in a shared VM environment or something. Memory is pretty much consistently flatline fast. But on the downside, it's volatile. DRAM, if you've looked at how it works, it's a capacitor and a resistor, and if you don't update that thing every however many milliseconds, or it just disappears. Your data's gone. So it disappears if the machine moves or if it sneezes or something, and it's expensive. That's the important thing. It's particularly expensive. So how expensive? This is a slide I stole from some guy down the bottom. Please check out his website. It's awesome. In this graph, which is totally vetted, RAM costs about $9 a gig, right? Compare that to NVRAM, which is like this fancy in-between kind of disk stuff at $2. SSDs, NVMe SSDs, which maybe the new modern laptops have, and the old SATA, like fake SSDs, down at about 40 cents per gigabyte in terms of storage. So $9 to 40 cents, that's huge. That's what, factor 20. But it doesn't stop there. Backblaze do these hard drive reports every year or so. They're amazing. If you haven't seen them, check them out. They talk about like failure rates for different brands, sort of stuff. You can see actual spinning disk, hard disk drives. They're a factor below again. So as we saw, SSDs 0.4 cents per gigabyte, $0.4 per gigabyte, 40 cents. SSDs down at the 2 cents, so 40 cents to 2 cents again. So 2 cents versus $9, that's a big scale. So that's why we can't have Redis everywhere, is because memory is expensive, and sometimes, especially with Kafka, you want to store a lot of data, and people have limited money. And sometimes it's important to retain that where possible. So fundamentally, is Kafka Redis? Of course it's not. As I said, look, none of the letters are the same. Disks change this because Redis is fundamentally limited to the in-memory portion that it can serve. So it's limited to, even your fattest Redis machine is going to be, what, 100 gigs of RAM? You don't tend to see them over that. But a 100 gig Kafka broker is tiny, right? We all run 2, 3, 5 terabytes easy. But because of the page cache, because of this kind of up-down is Kafka Redis, sometimes it can be. Like a request served from Kafka that's in page cache is about as fast as a Redis request. And we can be clever because brokers have RAM as well. And how we use that is the subject of this talk. Okay. When are we Redis? Let's talk in brief terms about the 5 modes that I've personally identified and guarantee are complete about broker I/O, so how brokers choose to use disks. First up, I've already described this, the file system cache. Just to be clear, this is not how any particular file system cache works. It's how most generally work. Some have optimizations, some don't, whether it's XFS, whether it's an ext4, whatever. The gist is OS uses spare disk space to retain spare memory space to retain recently requested disk data. I'm just going to read the slide because it's correct. OS retains recently read disk data in memory. If you ask that data again, it comes from memory, not disk, it's fast. If your broker or your machine is set to use all that memory for application data, there's no like unused RAM, so you get basically no page cache. The cache discards data, favoring new data, so it's always the most recent in general cases. And turns out your cache is pretty tiny versus compared to your disk. So if you're looking at your how many times do I hit the cache versus miss and have to go to disk, it's going to be, depending on your workload, very workload dependent, it's going to be likely you're going to miss a lot, especially as your cache gets smaller. Because your application uses memory. So this, for the purpose of this conversation, that's what a page cache is, a non-ZFS page cache. Right, so log appends. What happens in Kafka? Message comes in over the network, someone does a produce request to when a primary replica, blah, blah, blah. Kafka sticks it directly on the active log segment. It can do some fiddly bits with the timestamps or converting the record version or compression. It's kind of irrelevant. Mostly Kafka receives it, writes it to disk. It's an async write, which means Kafka allows the OS, or to be more specific, the file system, to determine exactly when to trigger the disks to run. You can you don't want to run it all the time. You kind of build up a bit, flush, build up a bit, flush, that sort of thing. Kafka lets the OS handle that. And in terms of performance, it's pretty consistent. If your buffer is not running out, spiky loads, buffer can help you smooth those out. Your performance will be pretty much limited by your disk latency. But it's pretty fast, and as I said, Kafka's async, so Kafka will accept the data from the producer before it flushes to disk. So if in fact there is a slight delay on your writing to disks, it's fine. The producers don't see that at all. So pretty consistent performance, and as we'll see later on, pretty fast. So the question then, in this case, for mode 1 of 5, log appends, are we Redis? Are we equivalent to Redis in this performance mode? And I would answer yes, we are, provided there is sufficient write buffer, because we're essentially writing it to RAM and it's later flushed to disk, but that's invisible to the producer, so we can look like Redis. Interesting question is to ask yourself, how many times is that data that was just written read back? Well, we know it's replicated, so all the other brokers replicating that particular piece of data are going to read that. Every client subscribed to it is going to read it again. And then if it's compaction-based, it's going to be reread. So it adds up. There's a difference between, there's something called like a write amplification. So one write can equal 5x reads easily. But then the question is, given how many times it's going to be read, is it going to be in cache? Because it would sure be useful if it was. And we'll see it's tricky to say. It depends on the timing, size of the cache, that sort of stuff. But it would definitely be useful. Mode 2, an in-sync consumer, right? Someone's keeping up. Client reads from a partition. Kafka says, hey, I see you're reading some data. I'm going to use the OS send file thing to just basically tell the kernel, say, hey, send this sector from this file descriptor to this network socket, which is also really a file descriptor. And just OS just handles all of that. It's smooth, it's beautiful. It's like the magic of Kafka. Since it's a live consumer, the data was pretty recently written, so fairly good chance it's in page cache. And we're really doing kind of a memory to network operation. So again, the question is, are we Redis in this case? Do we approximate Redis's performance behavior? I say yes, we are. And most importantly, since we're serving all the reads, in this case, from the page cache, the disks and their limited number of like I/O operations they can perform, they're all devoted to writes, and we've got perfect balance. Mode 3, a lagging consumer. So basically the same as before, except as we can see in yellow, it's probably not in page cache. It's on disk. Broker's got to go get it. Are we Redis? Absolutely not, right? That means the read has to hit the broker. Broker says, oh, you want that, do you? Fine. Goes off the disk and pulls it back. There you go. So now you're waiting on disk latency. Your disks are burning your IOPS on reads, not writes. And we're basically approximating an NFS. It's a disk-based access pattern limited by disk speed. Mode 4, a down conversion consumer. This kills us in Jet. Version 09 changed the on-disk version from something to something else, which means that if you write as the new thing and you ask for the old thing to read, the broker's got to read it in, convert it for you, and give it back to you. In short, it may or may not be in the page cache, but it's got to be read into the broker's heap, converted, sent over to the OS. OS has to copy it out of the heap into the OS space, sends it. It's like everything in this process eats your cache, your available RAM, and just makes everyone sad. And we're basically approximating MySQL, which is not what we want. Thankfully, we're moving further and further away from 0.9. Most clients shouldn't be issuing these old requests, but if you have older clients, or if in your logging you can detect when you're servicing an old request, it's important to know that this breaks the entire system. Recent versions of Kafka allow you to disable this. I like to think it's because we yelled at Confluent a lot. Maybe they had other people yelling at them, but definitely beware down conversion consumers. They break everything. And lastly, log compaction. It's been discussed already before. I presume you guys are familiar with it. The log segment grows to a certain size, tips over, the log compactor thread reads from it, rewrites it, blah, blah, blah. Are we approximating Redis in this behavior? And the answer is I haven't a clue. I don't think Redis does this at all. It's kind of a weird I/O mode. Right, so that's all of them. That's 5 modes. So in review, when are we Redis? When we're dealing with non-lagging consumers, people who are reading what was just written, almost guaranteed to be in page cache. And when we're doing writes and we have enough buffer, which should be most of the time. Like if your buffer is frequently emptying out, maybe you can smooth your load a bit, or increase your buffers, or increase your whatever. You can probably get to 2. You should be having 1 all the time. 2 you can probably get most of the time. As I said, a write is often read, 5, 6, 10 times. And if we can serve from memory, the question then is, what can we optimize so that we do? Just to cement this, think of this particularly evil case. The consumer wakes up, it's lost its offset somehow, and left them behind the fridge or something, and it's got to read from 0 on an entire topic. Maybe it's down converting at the same time. Every request that issues to a broker, except for the last 10, is going to be a page cache miss, which means all of the broker's IOPS are now spent servicing those reads and not writes. So that means produce operations slow down. The page cache on the broker is now caching this data that's only going to use for one person one time, which means it's evicting data that might well have been used for other people more recently. So your page cache hit rate reduces again. This means these reads that would previously have been served from page cache are now hitting disk, which means more reads are spent on disk. And it's less overall IOPS, so everything, pathologically, everything could stall to disk I/O speeds. Just because one consumer does something bad. And Kafka has no control over this because it's all OS handled. This is scary. Ideally, people say up to date, almost everything's a page cache hit served from memory. All the writes disks are used for the writes, which means your disks are maxed out on the write speed. If you lag and miss the cache, You don't significantly impact the write performance of the broker. That's good. Comes from somewhere else. Wouldn't that be nice? Log compactions don't like evict all this data because, I mean, who's going to read a compacted log? Typically no one unless they rebalance or restart up. Typically it's just kind of compacted for future use. It's entirely possible that's never going to be read. So reading into the broker's heap, which means there's less available RAM for the OS page cache, and then in reading it, evicting good data from the OS page cache at the same time is a double whack to your page cache hit rate. So ideally, log compactions wouldn't hurt us. And ideally, if a consumer for some reason has to do a full replay from offset 0, we don't want them to particularly impact performance for others. Right? This is where we want to get to. This is, I mean, to be simple, this is bad, this is good. Remember, as you might have guessed, I propose ZFS as a solution to do this. It's a file system. Let's talk about it. It has all of these features, right? We're only going to talk about 4 or 5 of them, but it's important to recognize this is a big... If you ever looked at JVM's internals, a JVM, of course, comes from Sun way back in the day. There's a whole bunch of tweaks. There's like engineering friendliness. You can do hot reloading of code. You can enable JMX metrics. Like if you really dig into it, the JVM is a beautiful piece of code that's really been one of the most battle-proven, I think, pieces of code on the planet, right? It's serious business, the JVM. ZFS is not particularly far from it, but focused towards file systems versus application runtime. I'm going to talk about 4 or 5 of these, but just bear in mind that I'm talking about a third of the feature set, a fifth perhaps. It does so much more, but not necessarily all relevant to Kafka. Super abbreviated history. Originally, 2001, Solaris. Open sourced when Sun went open Solaris. Linux couldn't use it because the license wasn't equivalent, but some guys did some fuse port and it kind of didn't work so well. FreeBSD, which is an amazing operating system you should all use, picked it up in about 2007. Apple tried it for a while. It was actually going to be the new file system on all your MacBooks until some political stuff happened, which you can Google for. Oracle closed open Solaris, and that gave rise to Illumos and OpenZFS, kind of split it off. And then in 2015, Canonical, the Ubuntu company, got enough lawyers to be bribed to understand that, in fact, it was license compatible. And then it just put it into the repo for Ubuntu 16.04. So if you have Ubuntu 16.04 system or later, it's like apt-get install ZFS, and you're done. It's in-kernel, it's up-to-date, it's supported, it's good. So how does ZFS help us in our plight? Primarily, it's the cache. It's this caching algorithm. And they call this the adaptive replacement cache, the ARC. At the bottom, there's a link to the paper, which these clips are from. And there's also a link to a well-known individual giving an amusing description of the paper, which I think everyone would enjoy watching. It's Brian Cantrell from Joint. Instead of a basic so an LRU cache will evict data that has been least recently used, LRU. So it focuses on storing the recent stuff. The ARC has a different approach to this. Importantly for us, it's scan resistant, right? If you just read a bunch of data through, but just one time, it doesn't like evict all the other data to store this stuff that was only good for one time. It's smarter than that. How does it work? It's read the paper, right? Super briefly. You have a list of recently accessed data, and you have a list of recently accessed data that was read more than 2 times. And then you have, and this is the key bit, 2 other lists that refer to stuff that you kicked out of those first 2 lists. Right? So the first 2 lists hold the actual data, second 2 lists hold like metadata about what you kicked out of those lists. So you're given some cache, let's say it's a gig. Divide it in 2, or whatever point. Below that point, used for list 1, above that point, list 2. So used once, used more than once. Every time you see a miss, right? Every time you cannot service data from list 1 or 2, check if you just threw that data away. Like you see, like, oh, sorry, I just threw it away. I didn't know you're coming. Sorry. If you did that, move C like 1 byte in the direction to favor that list. That's the whole thing. It's the whole algorithm. I mean, the paper is more complicated, right? But for our purposes, that's the whole algorithm. It allows us to be scan resistant. That's the important thing, which means replays from offset 0 and compactions, which is read in bunches of data, do not end up reducing the amount of like useful page cache we have. All right, superpower 2. No, superpower 1, 3. This is a graph from the paper that shows like page cache hit rate percentage for an LRU machine or cache running below, and the ARC is like clearly outperforming. What's important to note is this is incredibly workload dependent, incredibly. But Kafka's workload is like perfect for this sort of stuff. It's beautiful compared to like a Postgres database. A Postgres database which has lots of random reads and so on. Kafka's super. All right, what else can ZFS do for us? Set up a storage device, as I said, the instance SSD on a cloud VM to act as a second level ARC. So the first level ARC is in RAM. Second level ARC is on this super fast instant SSD. It's the fastest I/O you're going to get on a cloud VM is this local disk, rather than all the network attached other things. So it's as good as you can get. And in our case, ours go up to about 200 gigs. So if you've got 20 gigs of cache of RAM on your 32 gig broker, you have another 200 gigs of SSD cache, super fast SSD cache, just sitting there. It's slower than memory, of course, but it's way faster than disk. And critically, again, it does not mean that requests issued to this second level cache come from the I/O pool of your main storage pool, right? So it's another source of free I/O that you can use to feed the consumers. How does it work? Strictly, it's not a second tier of the ARC, because if you think about it, that would mean if you evicted data from the ARC, you'd have to then write it to disk, which means memory allocations for an application will be dependent on writing data to an SSD, which would be really slow. So that's a bad idea. Instead, there's like a process that runs in the background, like scavenges data that looks like it's about to be evicted and writes it to disk. And if it doesn't get it in time because someone allocates like 2 gigs, it's fine. It's a page cache hit miss. No one dies. It's my favorite feature in ZFS. It's my favorite feature. Superpower 3, LZ4. It's a compression algorithm. Kafka supports it natively. In short, it allows the disks to compress all the data written to them. We in Jet write a lot of raw JSON. So JSON compresses like 5x. So this means that basically we have 5 times more bandwidth of writes and reads along the way. And this affects the ARC, it affects the L2 ARC, it affects everything. It's always better for your producers to compress themselves, right? This is not better than that, but if for some reason your producers don't always compress, set this feature. It's like 10 gigs a second, single core throughput, so fast it's free. Anything that can be compressed becomes a linear factor increase in throughput based on the compression ratio. As I said, UTF-8 JSON reduces by fivefold. Increases hit rates because we store compressed blocks on disk and in the ARC and the L2 ARC. Last one, Superpower 4, the prefetch. If ZFS detects that you are reading a file in a certain pattern, it will infer that what your next likely read of that file is going to be. And since it's just a basic sequential read, it's pretty straightforward. If there is idle I/O on the disks, they're not being maxed out, it will actually go ahead and read ahead where you've actually read, stick it in the cache, and then if you actually do read it, it's like, oh, I already had that. There you go. Oh, you went to 1, 2, 3, 4. Oh, did you want 5? I thought so. There you go. It means that, again, fundamentally increases our hit rates. Almost every consumer is a sequential read, so it's a trivial prefetch. That's it. That's ZFS's 4 features. I'm not going to correct myself anymore. It's too hard. Right. What's I/O? 2 slides. I/O in 30 seconds. It's a disk read or a write. Different types of disks have different types of latencies that determine their I/Os per second. Local SSD, super fast. Remote, not so fast. Remote hard drive, not fast at all. Different disks can have different sizes. Your overall throughput is number you can issue per second times the max size of that. Super simple. If you're dealing with spinning disks, you care whether you're issuing reads in sequential sectors or randomly, because randomly will incur like a seek time. ZFS will handle all of that for you, right? That's all. That's disk I/O. We're done. We know all about it. What are some options for Cloud I/O? I'm talking about Azure here, which we use. We use ZFS's striping to make use of many disks simultaneously. Because of the design of Azure, it means every disk gets like 500 IOPS, regardless of the size. So a standard hard disk, 32 gigs, you can have 32 of them on some machines, cost you $1.50 a month, give you 16,000 IOPS. There's a transaction fee per read or write, which is complicated. I don't want to get too into, but just presume it costs about $25, right? It gives you a monthly total, $75 for, what's that? A terabyte of 16K IOPS, $75. That's pretty good. If you need faster latencies, you can step up to SSDs, you pay a bit more. You get actually less IOPS in this case. It's a strange balance. You have to work out for yourself which one works for you. I think the standard HDD beats the standard SSD. So you should probably only look at the HDD and the premium SSD. You still get less IOPS, but the latencies are fast. They've got some new Ultra thing. They want you to contact them for pricing. I did not contact them for pricing. And there's also got the instance SSD, which is this temporary one we talked about that we're using for the L2 cache. You get 12,000 IOPS on that disk alone. There's no transaction fee, and it's free with your disk, right? So on a machine that I'm going to show you the demos from, we've got 16K IOPS on the storage pool. We've got 12K IOPS on the L2 ARC. We've got however many bajillion IOPS the actual RAM can do. Sorry, how long does that mean? 10 minutes, okay, I'm rambling. I think standard HDD is a compelling use case. All right, super quick how-to. Install ZFS Linux. It's in native Ubuntu. Create the VM, stick as many disks on as possible. There's gotchas in Azure to do with premium disks. You don't always want to use that. That will reduce your actual temporary SSD instance size in some cases. Turn off any caching option. They say their cache is crap. Our cache is great. We don't want that stuff. Right? Create the pool, stick on 32 disks. If you do like a list block, you'll see like 32 disks fly by. In Azure, the SDB is always the instance SSD. You create the data drive, put some settings in, like on compression, and you can see here on the third last line, we list all the disks we want to add to the pool. ZFS just merges them all together. And then critically, we say, use the SDB as a cache. That's the L2 ARC. That, if you list the Z pool features then, will then show you the disks in their use. And then there's a few gotchas here. Refer you to the slides if you want to try it later on. But fundamentally, when you install ZFS, it will add a bunch of systemd services, which mostly work, but they do not handle the case where the machine moves, the VM moves physical host, which means it loses the temp SSD. So the pool can't mount after it comes back up if it's lost the temp SSD, because it says, hey, that disk disappeared. That's weird. I should probably not do anything. So remove these, add your own one, and that one just says, you know what, just remove the temp SSD when you start up for the first time and add it back, because it might have gone, why not? There's some tunings. I won't go through these, but the short version of it is tell it to use the hell out of the temp SSD, tell it to increase the queue length for the actual pool disks, and you can actually limit the ARC size, the page cache size. I like to set that to a fixed amount, which is basically total VM memory minus like 3 or 4 gigs for the OS and stuff, minus your Kafka heap max, and then that's the rest. And so you know what, ZFS, use the rest for cache. Super quick demo. There's an old tool called ArcStat that shows you exactly what your hit percentages are. It's still around, it's kind of useful. You can see like L2 read, L2 hits, L2 miss versus regular reads. But we've got cool features now in Prometheus and Grafana, so you can actually graph this. So here's a demo machine I did. You're looking at 95% plus page cache hit rate all the time. That means 95% of the time your hand is up, so you are Redis, right? 1 in 20, or 19 in 20. You can also measure the L2 ARC hit rate. It's a simple system from Grafana. And then just to prove that this works for the striping, here are some standard 16 disks, only 16, not 32 as I said before, $1.54 each, so that's $30 total, 25, and you're easily pushing 500 megs a second. You might wonder, how does this compare to ext4 and LVM? Here's exactly that, and it's a tiny bit faster, in some cases slower in others. It's about the same, right? You're hitting no performance loss for all the benefits. And in this particular case, I was doing 150,000 1K messages per broker. That's what it was syncing. So this, again, for $32 worth of I/O. Couple of caveats, super quick. There's something called a ZIL on ZFS. It's like the L2 ARC, but for writes. Don't do that. It doesn't work for Kafka because all its writes are async. And if the host moves to another physical host, it's a lot trickier to recover. So don't get tempted by that. Deduplication is a ZFS feature. Don't do that. Huge memory hog. You shouldn't be producing duplicate message anyway. When you're building your pool, do not add the temporary instance to the pool. Always say cache and in this instance, because it's actually quite hard to take a device out of the pool. So that will make you sad. Don't do that. ZFS has a feature called snapshots, which allow you to keep persistent copies of data. If you're using retention bytes, which I presume you are, that means that data will never be deleted, and eventually your actual pool will run out of space. So that's a bad thing. And there's features as well around RAID-Z and duplication, which I suggest we don't use because probably your cloud provider has this kind of triple redundancy storage going on anyway. Almost done. A couple of future ideas you could try. What if you mirrored the instance SSD and the backing SSD? Could you, in fact, have all your writes and reads go to the instance SSD, but then have it slowly replicate out to the slow pool? That would mean your broker size is limited, but it's basically a super fast ultra SSD for almost nothing. You can set on ZFS copies equals 2, which means every time you write to the pool, it will actually write it in 2 places, right? Which means your storage capacity is halved. But maybe when you read back, it means you've got double I/O for reads. Maybe your reads go really fast. ZFS has guaranteed data integrity. So can we skip startup verification on Kafka, increase startup speed? Other tweaks like this. Something to consider. I'm going to play with this. Feel free to contact me. That's the end of my talk. Thank you very much.
So we have time for questions.
Hi, great talk. I have
you.
one question. So Kafka can actually use off-heap memory to store a bunch of log segments in off-heap memory. So I was just wondering the trade-off between using a page cache to do that versus tuning Kafka to just store it in off-heap. As in, why use a file system page cache when I can tune Kafka to just keep that in JVM off-heap memory?
I haven't explored that much, so I couldn't give you an intelligent answer, but I'd love to speak to you afterwards, if that's okay. My gut response would be that there might be some benefit to the caching algorithm and maybe the compression, but there might be benefits to your method as well, so I couldn't say for sure. But I'd love to speak to you afterwards.
Hi, I actually implemented something pretty close to this but on Amazon, so I just thought I'd share real quick. Going from D2s to I3s and just using the local NVMe for the storage layer, it only increased cost by about 8%, but gave a humongous RAM cache to Arc, and the performance was incredibly faster. It's made a huge stability factor. So if you're Amazon instead of Azure, take a look at that.
And that's for Kafka brokers?
Yes.
Yeah. Do you track your hit rates?
Yes.
Track your hit rates, right? You should know where your hit rates are at 11 o'clock at night. Please.
Hi, great talk and great experimentation. Do you have the benchmarks that you have published somewhere that we can reproduce?
That's the bench. They're in the slides. That's the benchmark command. I'm going to put up a blog post for the full details afterwards. Here are the versions I was using. If you're using FreeBSD, like the Arc is integrated into top. I thought that was cool. And this is the little lab environment and the machine sizes I used. I'll put all this together, but for basic versions, you can look at this. Every disk was like the cheapest Azure, 32:1. And in this case, brokers were D12s and clients were D2s. One interesting thing on Azure is that these two machine sizes have the accelerated networking feature, which means there's a lot less, it's SR-IOV stuff, so you can push more bytes than you normally would. But since we're testing the file system, not the network, I thought it was important to go fast.
Perfect, thank you.
Thank you. Thank you.